Hello, I am Seema and welcome to part 11 of the chapter Haloalkanes and Haloarenes. In this video, I'm going to tell you about the physical properties of haloalkanes and haloarenes. And before I come to the actual properties, I have a suggestion for you. And that is how I did it. Like, if I wanted to memorize the properties of something, I would imagine that substance to be a person, or an animal, or a plant, or something. I would always try to either make it one person or a pair of friends, and two friends, because when you talk of bonding, it becomes easier to talk of two friends. So just imagine in your mind's eye, try to think of someone whom you will be giving these properties to. So whenever during the exam, when you get a question on this particular topic on the properties, what should come into your mind is that person, or the pair of friends, and automatically the properties that you have learned, and those you have attributed in your mind to those two people or that one person, they would automatically come into your view, and it will be very easy for you to remember that. So in chemistry, if you try to memorize things thinking that they are dull, drab, non-living material matter, it becomes a little difficult to memorize because it's a little monotonous, it's a little boring, and there's too much of detail, so it may be a little confusing. It always helps to make it interest it up a little. Try to think of any way of memorizing it and then do it. So let us now come to the properties, the physical properties of haloalkanes and haloarenes. Here I'm going to imagine a pair of friends, and that pair of friends is in your class, right? And this pair of friends, they sit in a corner, and they're not very noisy. They're not really you will not find them pushing in everywhere. They're just friends, and they're silent, calm, peaceful people. So alkyl halides are colorless. There's no color to them. There's no flashy things about them. They are colorless. They're very simple. So alkyl halides are colorless when pure. When they are pure, they are colorless. But when they are present in a group, they might show color. So they are colorless when they are pure, but if you take them out in the sun, if you take me out in the sun, my face turns red and I get so angry. I don't like the sun at all. So, cloudy. So I don't like the sun at all. Therefore, my face turns red. It is something like that, this pair of friends, when you take the bromides and chlorides, the name of your friends is, these friends may be bromide and chloride, they have multiple names. So the bromides and chlorides, if you take them out in the sun, they start developing color. They don't like the sun. So let us assume that they don't like the sun and they start turning red and brown in the presence of light. The second property is that many volatile halogen compounds have sweet smell. So when you go past this pair of friends in the classroom, as you just pass through them, you realize that they have a sweet smell about them. So imagine these people to have a sweet smell, a nice presence, right? So they have a sweet smell. About the physical state, when you talk of physical state, it is very much logic, The smaller the molecules are, and the more are the chances of that substance being gaseous in nature. The larger the molecules, the chances are that it would be liquid. And if the molecules are really large, the chances are that it would be a solid. This is common sense. And the same is seen in the case of haloalkanes and haloarenes also. The lower members, for example, methyl chloride and methyl bromide, they have only one carbon atom, one methyl group, and chloride and bromide, they are gaseous in nature. To the extent that if you come to ethyl chloride is also gaseous in nature. Because it is small, the ethyl group is small too, and chlorine out of all the halogens is pretty small. Therefore, that would also be gaseous in nature. The other chlorofluoromethanes, some chlorofluoromethanes, they are also gaseous in nature. But higher members, chloro, both chlorine and fluorine are the lower members of the halogens. So if you have chlorofluoromethanes, they may also be gaseous in nature. But the other higher members would either be liquids, and even still higher members would be gaseous in nature. So when you talk of physical states, methyl chloride, methyl bromide, ethyl chloride and some chlorofluoromethanes are gases, and higher members are liquids or they are solids. You know, I get requests sometimes that children want to take screenshots or maybe copy down what I write on the board during the class. So they suggested that if I just step out of the frame once, they can take a screenshot, it helps them. So I'll just wait for you to take a screenshot and I'll continue with the next property. So the next property is polarity. Haloalkanes and haloarenes are polar in nature. What do you understand by this? You know, halogens are those elements which fall to the right of the periodic table. And in a period, the atom that is the halogen atom is the most electronegative. Being the most electronegative, it has a tendency to pull the shared pair of electrons towards itself. So we find that in comparison to the halogen, the carbon always is more electropositive. Therefore, the halogen will have a tendency to pull the shared pair of electrons towards itself, making it partially negatively charged, while the carbon becomes partially positively charged. Therefore, when we talk of haloalkanes and haloarenes, they are polar molecules. When you imagine these as the pair of friends that I am allotting the properties to, one of the friends is kind of has a more positive attitude towards life, and the other is slightly negative. So there is a polarity in their attitudes. So they are friends, they are silent, they may have many things that are similar, but they are a polar pair, right? So polarity, they are polar molecules. Now, how would the polarity be affected? From fluorine is the smallest atom. Fluorine, chlorine, bromine, iodine. The electronegativity decreases as you go from top to bottom in the periodic table. So fluorine is the most electronegative. So the polarity of fluorides would be the highest, and polarity of iodides would be the least. When you talk of bond length, fluorine is the smallest atom and iodine is the largest. So fluorine would form a bond length which would be the shortest because fluorine is the smallest atom. The distance between the nucleus of carbon and fluorine would be least. Then would come chlorine, would be slightly larger, bromine would be even larger, and iodine is the highest. So bond length increases from the fluoro compound to the iodo compound. Therefore, the bond enthalpies, what is bond enthalpy now? Bond enthalpy is the ease with which you break the bonds. So, as the bond length increases, it becomes easier and easier to break the bond because the nuclei are far away, the attractions, the further away the two atoms are, the lesser attraction they will experience. Imagine it to be a magnet and a nail. The further away the magnet is from the nail, the lesser attraction the nail feels from the magnet. So it becomes easy to separate them. But if they are kind of joined, stuck together, you have to apply a little force to separate them out. It's the same thing. Bond enthalpy is the amount of energy that is required to separate out the two atoms. So bond enthalpies, they will, since the distance between the length of the bond keeps on increasing from fluorine to iodine, the bond enthalpies would keep on decreasing. You'll need less and less force or energy in order to separate them. If you talk of dipole moments of these haloalkanes, what is dipole moment? Dipole moment mathematically is charge into radius. And when you talk of charge, the greater the electronegativity, more will be the charge. So charge into radius. Fluorine has a very high charge because it is the most electronegative. But it has a very small radius, due to which the dipole moment of the fluorocompounds would be really low. CH3F has got a very high charge but very small radius. Therefore, its dipole moment is 1.847 dpi. This is because since the radius is less, therefore Q into R is also less. Q is charge and R is radius. If you come to methyl chloride, the dipole moment of methyl chloride would be 1.860 dBs. Now what do we see? It is greater than that for fluorine. Why? When you talk of charge, the charge may be slightly lesser, but the radius is more. And since the radius is bigger, therefore it has dipole moment is higher. Then you come to CH3Br, it is 1.830. Again, do you see both the things are affecting? Here the size is still bigger. The size is bigger, radius is bigger, but charge has decreased. Therefore, it has a value of 1.830. And iodide is the least. It will be 1.636. So charge and radius, both of them together, the combined effect of these causes the dipole moments of the haloalkanes. The next property that we come to is the melting points and the boiling points. Again, melting points and boiling points depend on, when a substance melts or boils, there is no chemical change that is occurring. The molecules are bound together by some forces of attraction, which are usually known as van der Waals forces of attraction. And these forces of attraction have to be overcome in order to change the state from a more solid state to a lighter state, like a liquid or a gas. So the melting points and boiling points will depend on the forces of attraction that are present in these molecules. So let us see how are the melting points and boiling points affected. Now, this pair of friends that you have been imagining, how well do they gel with other friends of their kind? And how attractive is it? How much attraction keeps the entire group together? That will decide the melting point or boiling point. Now, these molecules are polar in nature. Anything that is polar should have a higher melting point or boiling point, because wherever charges are developed, positive and negative, a charge separation occurs, there a little ionic character develops. And electrostatic or Coulombic forces are always stronger than simple covalent bonds. Wherever there is electricity, there is more attraction. So due to polarity and higher molecular mass compared to the hydrocarbon. If you take a simple hydrocarbon which does not have the halogen, all atoms are carbon and hydrogen, and it is non-polar in nature. So in comparison to those, the corresponding haloalkane will always have its melting point higher. Due to polarity and higher molecular mass compared to the hydrocarbon, the intermolecular forces, what are the intermolecular forces? Dipole forces. The dipole forces are not there in the hydrocarbons. Why? Because they are non-polar in nature. But here, even if the instantaneous dipoles that are produced, of course, they would always be there. But the dipole moment in the case of polar molecules would definitely be higher. And van der Waals forces are there. So we say due to the polarity and higher molecular mass compared. Why higher molecular mass? Because if you take a hydrocarbon, you are replacing a hydrogen with any of the halogens, and the mass of hydrogen is 1, while the mass of the halogens definitely is much higher than that hydrogen. So any molecule, even if it is single substitution of the halogen, it would be heavier. So greater the mass, more would be it would affect the melting point and boiling point. So, due to polarity and higher molecular mass compared to hydrocarbons, the intermolecular forces, that is dipole-dipole moment and van der Waals forces, are higher in haloalkanes. Therefore, the boiling points of chloro compounds, bromo compounds and iodo compounds from the corresponding hydrocarbon would definitely be higher. When I say corresponding hydrocarbon, I mean if you have methane and you have methyl chloride, the melting point and boiling point of methyl chloride would be higher because it has chlorine in place of one of the hydrogens. The molecular mass is more, the molecule is polar in nature, so there is attraction, so it will require more energy to separate the molecules. Now, I have written here that attractions become stronger for bigger molecules with more electrons. As the molecule becomes bigger, like we are going to higher haloalkanes, as the molecule becomes bigger and bigger, the molecules, if the size of the atoms is increasing, the number of shells is increasing. If number of shells is increasing, obviously the number of electrons is also increasing. If you have more number of carbon atoms in the chain, again, you have those many more electrons. The larger the number of electrons, more energies of attraction and repulsion come into play. So we say attractions, repulsion, of course, they will always, the molecules will always adjust themselves in such a manner that repulsions are minimum. But with the increase in size, attractions go on increasing. So we say attractions become stronger for bigger molecules with more electrons. And if attractions are more, obviously the melting points and boiling points would be higher, because you'll require more energy to overcome those forces of attraction. If you have the same alkyl group and you have different halogens, how do you think would the boiling point differ? For example, if you have iodine, iodine is the largest, is the heaviest, and I told you anything that is bigger and which has for bigger or more atoms in the molecules, more electrons would be there, therefore it would have a higher boiling point. Therefore we find that any alkyl group, the alkyl R is the same, the iodide of that hydrocarbon would have the highest boiling point, then bromide, then chloride, and then fluoride. So the larger the size of the halogen, the more would be the boiling point if the alkyl group is the same. Why does this happen? This is because with increase of size and mass, yes, this is interesting. As the size and mass increases, the van der Waals forces, they depend on the mass of a substance. The greater the mass, the higher are the van der Waals forces. The greater the surface area, higher are the van der Waals forces. So what are van der Waals forces? They are forces of attraction which come into play when something interacts with something else. When anything interacts with a neighbor, the van der Waals forces come into play. I am being attracted by the board is being attracted by me. These are forces which are known as the van der Waals forces. So the larger the surface area, the larger a molecule, the heavier a molecule, obviously they would be more, it would be more solid, and therefore it would have and when I say solid, I don't mean the physical state. It would have a greater interaction with the surroundings, and therefore the attractions, the van der Waals forces of attractions would be higher. So we say this is because with increase of size and mass, the van der Waals forces increase. Let us now talk of the boiling points of isomeric haloalkanes. What are isomeric haloalkanes? Isomeric compounds or isomers are compounds which have the same chemical formula but different structural formulae, which means the arrangement of the atoms is different. So you've studied about isomers. Now this is bromobutane. Bromobutane has three different isomers. The first is 1-bromobutane, this is 2-bromobutane, and this is 2-bromo, 2-methyl propane. 2-bromo, 2-methyl propane. Right? So what has happened? All of them have the same formula, only the structure is different. And now if you pay attention to the structure visually, this is a longer molecule. This has a branch, so it appears to be a slightly condensed. It is a smaller molecule because although it's not that long, the surface area has decreased with the branching. And here it appears to be a sphere. It's more like a sphere, right? Because here, I call it a sphere because you see here the carbon, the three hydrogens will be striking out like this to form a tetrahedron. The three carbons here would be forming. So this would appear to be a sphere, more like a sphere. So a sphere has the minimum surface area in shape. So when you have the bromobutane, which is linear, it would have maximum surface area. More the surface area, more are the van der Waals forces. Smaller the surface area, lesser are the van der Waals forces because the lesser of the molecule is coming in contact with the surroundings. This carbon is not actually coming in contact with the surroundings, so it is not going to contribute to the van der Waals forces. So we find that as the molecule, as the branching increases, the boiling point decreases. Why? Because when branching increases, the surface area decreases. And when surface area decreases, the van der Waals forces decrease. And when van der Waals forces decrease, the boiling point also decreases. So we said boiling points of isomeric haloalkanes decrease with the increase of branching. Now I leave it to your imagination to imagine how you're going to apply it to those friends. Then if you have isomeric dihalo compounds, di-substituted compounds. So you have benzene, and in which there are two halogens substituted. So you may have 3 isomers. One is 1,2, that is ortho. The 1,3 substitution is meta, and 1,4 substitution is para. So you can have 3 types. The isomeric dihalobenzenes would usually have almost the same boiling points and melting points. But the melting point increases in para. In the case of para isomer, the para isomer is more symmetrical. The molecule is more symmetrical. Since it is more symmetrical, when we are talking of melting point, it means that in the solid state, the para compounds, they tend to form better arrangements to form solids. A better packing is possible. Where you have meta and ortho, the molecule is kind of lopsided, it is not symmetrical. And since it is not symmetrical, the arrangements will not be so good. But when you have a symmetrical molecule, the arrangement will also be symmetrical, there will be more system, therefore it will be more stable. So we find that in the case of para dihalosubstituted benzene, the melting point of the para compound or the para isomer would be higher in comparison to the meta and ortho and meta. Then we come to the next property, that is density. Density depends on how heavy a substance is. The heavier it is, the more dense it will be, the more viscous it will be. So density is mass per unit volume. So obviously the heavier it is and the more condensed it is, it will be mass per unit volume, that would be the density. So if you compare the corresponding hydrocarbon, if you substitute a halogen, the mass increases. If the mass increases, it is natural that the corresponding halogen derivative of the hydrocarbon will always have more density than the hydrocarbon. And hydrocarbons usually, float over water. And since these are denser, they have a tendency, the same corresponding halogen substitute will sink in water. It would be heavier, it would be denser than water. So it would be heavier than water. Density increases with increase in number of, now what would density depend on? Again, the mass. If the mass of the molecule, how can it increase? One, either the number of carbon atoms in the molecule is more. So with increase in number of carbon atoms, that is, if you have methyl, you have ethyl, propyl, butyl, as you keep increasing the number of carbon atoms, the density will go on increasing. So density will increase with increase in number of carbon atoms, and with the increase in number of halogen atoms. If you have 1 chlorine, you have 2 chlorines, you have 3 chlorines, substituting obviously more the halogen atoms, the more will be the mass or the atomic mass of the halogen atom. If you have fluorine, which has the least mass, then chlorine, then bromine and iodine. If you take 4 compounds with the same alkyl group, you will find that iodine will be the most dense because that has the heaviest halogen atom in it, even if the number of halogens is the same. So these are the factors that would affect the density. One is the density would be more with increase in number of carbon atoms, in the increase in number of halogen atoms, or the increase in the mass of the halogen atom. Now we come to the last physical property, that is solubility. How well do they dissolve? It has been found that usually we say that polar solutes dissolve in polar solvents. So most of the ionic compounds, they dissolve in water because they are polar in nature and they would easily dissolve in water, which itself is a polar solvent. But it has been found that haloalkanes, even if they are polar in nature, they are sparingly soluble, barely soluble in water. They do not dissolve in water. What is the reason for it? For any substance to dissolve in water, anything that is dissolving, the basic principle is, the energetic principle is that the amount of energy that is released in the end when the substance, the final product is formed, should always be more than the energy that is given to carry out that change. If you dissolve it in water, now these molecules have to overcome the forces of attraction between themselves, their own van der Waals forces, and they have to give out energy in order to break the attractions between the water molecules. And water molecules don't have just van der Waals forces. They have hydrogen bonding also, which is an extreme case of van der Waals forces. So they have hydrogen bonding, and these hydrogen bonds also have to be broken. Hydrogen bonds are such strong van der Waals forces that they have been named hydrogen, they have been called by the name of a bond, while actually there is no bond there. Yet we call it a bond because the attraction is as strong as that would be of a bond. Now the hydrocarbon has to break away from each other. It has to break the water molecules also, so that it takes the place between the water molecules. And in the end, when it releases energy, the energy released should be so much on the product formed. It should be so much that it leads to stability. But the problem is that these molecules, they do not have as much energy in order to overcome. They might overcome their own van der Waals forces, but they are, and the water molecules, the van der Waals forces of water molecules, but they cannot break the hydrogen bonds of the water molecules. And therefore, since they are unable to break the hydrogen bonds, the water molecules will not move away. If they will not move away, these molecules cannot take the places in between and dissolve. So they are sparingly soluble in water. Very slightly soluble in water. In order to dissolve, the energy required to overcome the attractions between the haloalkanes and hydrogen bonds of water. There is energy which is required, but this energy released on new attractions. When the product finally it has been formed, you force it to dissolve it and you force it to break the hydrogen bonds. In the end, when the product is formed, the dissolved hydrocarbon, it should release energy. That energy released should be more than the energy that had to be given to carry out the change. And that is not released. That much energy is not released. So energetically, dissolving haloalkanes is not feasible. So energy released on new attractions is less. However, they are soluble in organic solvents. Why they are soluble in organic solvents? Because in the case of organic solvents, the amount of energy, the van der Waals forces of haloalkanes and the other organic solvents is kind of similar. So it's not that difficult. The energy barrier is not much. They don't have to overcome that much, give so much of energy or absorb so much of energy to first break the hydrogen bonds. The energies of the molecules is kind of similar, so it's easier to blend in. And that is what solubility is. So these were the physical properties of haloalkanes and haloarenes. And with this, I'll wind up today's video. If you found it helpful, give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.